Let's take a journey together, not to a distant star, but to a place far stranger, the very heart of reality itself. We are going to explore a phenomenon so bizarre, so contrary to our everyday experience, that Albert Einstein himself, one of the greatest minds in history, could not bring himself to fully accept it. He famously called it spooky action at a distance. We call it quantum entanglement. Imagine you have two coins. These are not ordinary coins. They are special quantum coins. You put them in a machine that flips them and then sends them flying in opposite directions at nearly the speed of light. One coin travels to London, the other to Tokyo. Now, you know that if one coin lands on heads, the other will, with absolute certainty, land on tails. Their fates are linked. The truly strange part is this. Until you look at one of the coins, neither of them is heads or tails. They exist in a ghostly, uncertain state of pure potential, a blurry superposition of both possibilities at once. It is only the act of observation, of looking at the coin in London, that forces it to choose a state. Let's say it chooses heads. The instant it does, the coin in Tokyo, thousands of miles away, simultaneously and instantly chooses tails. This is the unsettling reality of quantum entanglement. Two particles, like our two coins, can be created in such a way that their properties are intrinsically linked. They become part of a single, unified system, no matter how far apart they travel. If one particle is measured to be spinning up, its entangled twin, whether it's in the next room or in a galaxy a billion light years away, will instantly be found to be spinning down. The information about the first particle's state seems to travel to the second particle faster than the speed of light. This is what bothered Einstein so much. His own theory of special relativity had established the speed of light as the ultimate speed limit of the universe. Nothing, no information or signal could travel faster. Yet, here was a phenomenon that seemed to mock that cosmic law. It was as if the two particles were communicating instantaneously, whispering secrets to each other across the vast emptiness of space. How could this be? For decades, physicists wrestled with this paradox. Einstein and his colleagues proposed a more common-sense explanation. Perhaps, they argued, the particles were not communicating at all. Perhaps the information about their final states was already programmed into them from the moment they were created, like a set of hidden instructions. Imagine you put one black glove and one white glove into two separate, identical boxes and mailed them to opposite ends of the world. When your friend in Tokyo opens their box and finds a white glove, they instantly know that you, in London, have a black glove. No spooky action is needed. The outcome was predetermined from the start. This became known as the theory of hidden variables. It was a comforting, logical idea, and for a long time, there was no way to prove it right or wrong. The debate remained a philosophical one, a clash of intuitions about the nature of reality. Then, in the 1960s, a physicist named John Bell devised a brilliant mathematical theorem. Bell's theorem, in essence, provided a way to experimentally test the difference between Einstein's hidden instructions and the spooky, instantaneous connection of quantum mechanics. It was a test that could be performed in a laboratory. Over the following decades, physicists like Elaine Aspect, John Clauser, and Anton Zeilinger, who would later win a Nobel Prize for their work, performed increasingly sophisticated versions of Bell's test. They created pairs of entangled particles and measured their properties at different angles, and the results were stunning. Time and time again, the experiments proved Einstein wrong. The universe is, in fact, as spooky as quantum mechanics predicted. There are no hidden instructions. The particles do not know their state until the moment they are measured. The connection between them is real, instantaneous, and completely independent of distance. It's not a signal traveling through space as we know it. It's something deeper, a fundamental property of the fabric of space-time itself. It's as if on some profound level, the two particles are not separate objects at all. They remain, in some mysterious way, a single entity, occupying two different points in space. To touch one is to touch the other. This isn't just a bizarre intellectual curiosity. Entanglement is now at the heart of revolutionary new technologies like quantum computing and quantum cryptography. But its philosophical implications are what truly boggle the mind. It shatters our classical view of the world as a collection of separate, independent objects. It suggests a universe that is profoundly interconnected, a holistic web where what happens over here can be inextricably linked to what happens over there. We are left with a reality that is far stranger than we could have imagined, a reality where distance is not the barrier we think it is, where objects can lose their individual identity and merge into a single, correlated whole. Einstein's spooky action at a distance is not a flaw in the theory. It is a fundamental feature of our universe. It's a ghostly, unsettling, and beautiful reminder that the cosmos is under no obligation to make sense to our limited everyday intuition.